On our previous videos, we looked at various examples of how operators are applied to a particular function, like for example a, which is an operator acting on a function, and that results in the generation of our eigenvalue, which is also an observable, and this generates our eigenfunction. So we took note that a is actually an observable, and this observable is kind of a classical representation in here of the operator that is actually used in this particular example. And take note in here that what is happening now is that our operator's goal is to be able to act on this function in order for we to actually extract an observable that is actually unique to this particular operator. And this is going to be important in later videos, but in here we're going to see more into how operators actually act on function or functions. So in here we're going to take note of the linear operators which must satisfy two conditions, and these two conditions right here are really important, which will actually guide us into solving more problems in terms of Hamiltonian operators and getting into various interesting energy results, which are actually eigenvalues of the process. So coming in here, we're going to see one case scenario where we have our operator acting on two functions, and take note that these functions here are actually arbitrary functions, and what we'll notice here is that a here is acting on this function, and this is going to also act on that function. This is kind of an expansion process, and what that results in is the formation of two, I would say, variables, where we have our operator a acting on the f at x function plus a acting on the g at x function. So the f and g here functions are actually arbitrary functions, and I would say in this case they are actually eigenfunctions. And from our previous videos we looked at eigenfunctions, specifically the ones with the e to the 2x, where we're able to regenerate this particular function in here, but we get our eigenvalue, which is going to be, well, you guys can solve it for yourselves, and you guys can actually determine based on the arrangement of this particular operation right here. So diving well into this particular video, that is one actually step of actually generating the condition for how the operator is acting on a particular function. Now the second one in here is actually when we have our operator acting on, I would say, a constant that is applied to a particular function. So in this particular case, what happens here is that since our constant is right there, constant doesn't do anything when an operator is acting on it, because at the end what we get is 0. So rather what happens is that we take that out of this particular expression here and it stays the same, and what that results in is that we can now allow our operator to act directly on our eigenfunction. So in this case we have our a acting directly on our eigenfunction, which is an arbitrary function right there. So those are the two interesting ways by which we can actually see how our operator is going to be acting on an eigenfunction or functions. And take note here that c here is actually a constant, so once it's a constant you just put it at the front of the variable and allow your operator to act directly on your eigenfunction or your arbitrary function. So that being said, we're going to look at a specific example where we actually have, I would say, a expressed as x multiplied by d to the dx. So this is going to be applied to this particular function, and we're going to see what that leads. So in this case, what happens now is that a is going to be multiplied by our f at x function plus our operator will be acting on our g at x function, and what that results in is that x by substitution is going to be multiplied by d applied to the f at x function over d at x plus x multiplied by d applied to our g at x over the x function. So by that way, what happens now is that this operator here is going to be applied to our function right here to actually generate an observable that is a great representation of our a function. And once we have series of observables, by adding we actually result in our observable that is a great representation of our operator right there, which is a. So that being said, we're going to look more about one note you need to take note of right here. So one thing you have to take note is that when you have a plus b, which are operators, multiplied by c, it's actually different and is not equal to where c is going to be acting on a plus b. Now the reason why is because by expansion what we have is a acting on c plus b acting on c, and take note that in here we're going to be applying all these operators to, let's just say, our eigenfunction. So this actually shows that it's still not equal to c multiplied by a plus c multiplied by b operator, and take note that this is still applied to our eigenfunction. So in this case, what we're noticing now is that if you extract, let's just look at this two here, this arrangement where b operator c is going to be acting on f versus that of c b acting on the same operator function, what we notice is that when b is acting on f, we get a different value here from when c is acting on f at x. So when that happens, we actually result in a number where, or a function where b then acts on this later, and on the other side we have c acting on this. So what that means is that once we get a different value from the first step here, there's no way your result here will actually make the result of this to be equal to each other. So that's about it for this little bit of understanding on properties of operators, where we're looking at how operators is applied to a particular function or series of functions to result in the generation of our function, but spitting out observables that are classical and a huge representation of our operator, which is quantumly inclined. So all the same, please hit the comment down below, let me hear your thoughts about this, share with your friends, but that way I can talk to you all later. Stay smart and believe in yourself.